So, good morning, everybody. Welcome to the second day of the celebration of the 25th anniversary of the Clay Millennium Problems. So this morning we're focusing on the Poincaré conjecture, which, as you all know, is distinguished from the other Millennium Prizes by the fact it's been solved, famously by Gregory Perelman around 2004, 2005. And like all great advances in mathematics, it opens doors in two ways. There are the consequences of what he did and the consequences of how he did it. And correspondingly, we have two talks this morning. In terms of what he did, in the context of three manifolds, at the time the Millennium Problems were framed, because the Poincaré conjecture was already firmly embedded in Thurston's geometrization program. And of course, what Perelman really proved was Thurston's geometrization conjecture. But Perelman's achievements sit centrally in a landscape of remarkable advances by many different people in the last 20 or 30 years in our understanding of the nature of three-dimensional space, three-dimensional manifolds. And one of the great lessons of that advance is the central role that hyperbolic geometry plays in dimension 3. And we're delighted to have as our speaker this morning one of the good experts in hyperbolic geometry in dimension 3, Jeff Brock. In his spare time, Jeff runs science and engineering as dean of Yale, but more importantly for us, he is the Massey Professor of Pure Mathematics in Yale, and somebody who, in a distinguished career that took him from a PhD in Berkeley with Kurt McMullen in '97 through Stanford, Chicago, and Brown, and now Yale, is somebody who's made profound understandings to our understanding of three-dimensional manifolds. So we're delighted to have him. Please welcome Jeff Brock.
All right. Thank you very much, Martin, for the introduction and for the organizers for the opportunity to speak at this distinguished event. It's a real honor. I suppose some thanks is also due to the United Airlines ground crew that managed to limit my stay in Newark to 24 hours. But it's really a tremendous opportunity for me and the opportunity to frame the work that Perelman did, although we'll hear in more detail what he actually did, but in the context really of the work of Thurston to set out a program for understanding the geometry and topology of three manifolds. There was a great deal of work underway at the time at the announcement of the geometrization conjecture and its proof, to understand three manifolds in a deep way across the board, not all focused on the proof of the Poincaré conjecture, the geometrization conjecture, but I think that work has continued much in the way that once we knew what the uniformization theorem for Riemann surfaces, what shape it might take, there's still plenty of work to do to understand moduli of Riemann surfaces and moduli spaces of Riemann surfaces. So I suppose that's the sort of meta comment here in regard to the state of the field. But I'll try to dig into some interesting questions I find interesting that linger and some developments subsequently. So the Poincaré conjecture actually was false. So what he actually conjectured was that each closed three manifold with trivial first homology is homeomorphic to the three-dimensional sphere. Now, to his credit, he had just invented homology, so he was working it out. He published this as a theorem and then discovered the Poincaré dodecahedral space, which is the first example of a homology sphere in dimension 3. It's a very simple construction where you glue opposite sides of a dodecahedron. And what's also remarkable here is just the range of shapes that these homology spheres can take. We now know lots of examples of homology spheres that have wild geometry. So he asked the real conjecture as a question, is each closed three manifold with trivial first homotopy homeomorphic to the three-dimensional sphere? So Thurston, in trying to understand three-dimensional manifolds in a deep way, arrived at this from a different point of view. So Thurston was, a great inspiration to all of us, in part because of his kind of generally non-standard approach to interacting with, well, society, but the mathematical community in particular. And the way he writes is sort of very descriptive and non-standard. But you sometimes have to read things a few times to really get at what the mathematics is underneath it. And this is no exception. So his work set the stage for a really broad point of view on three manifolds. And he formulated the geometrization conjecture that the interior of every compact three manifold admits a decomposition into pieces, each admitting a geometric structure. So you have to unpack what all of these terms mean. But it took, I would say, it was close to 25 years since after that was formulated for an approach that had been worked on extensively by Richard Hamilton to be resolved by Perelman, and we're going to hear another lecture later from Bruce Kleiner about exactly what that was all about and what kind of new questions that method opens up, and I will be interested to hear the state of things. So Perelman resolved this somehow in the dark of night, and it appeared on the preprint server one fine morning, and there we were to try to understand it, and Bruce's efforts yielded a great deal of understanding of how this works. But the challenge is, I would say, that the flow itself is not particularly it's not sort of at a first principles level adapted to hyperbolic geometry. So the work that we were doing to try to understand the hyperbolic geometry of three-dimensional manifolds was somehow orthogonal to that. And so it's an interesting question how that flow can be adapted to questions that are purely hyperbolic in nature. But let's just try to get through the statement, because I know, there's sort of it's like being a two-dimensional animal. Like, you think everyone around you understands what you're doing and your motivations, and then there's this whole world that doesn't think about three manifolds all the time. So I have to try to become a three-dimensional person to explain this. So the prime decomposition is really the first step. Okay, so you're given a three manifold, and you look around for spheres that are non-trivial in the topology of this three manifold, in the sense that they cut the manifold into two pieces where neither piece is a ball. Okay, so it was Naser who proved that you can do this in a way where the summands, if you will, you get a sort of a prime, you connect these things with something called the connected sum operation, and the summands are all unique. And once you're done cutting along these essential spheres, you cap them off each with a ball, and then you're left with a new collection of manifolds, and that's the prime decomposition. There's a second topological decomposition for the statement of the conjecture, which is called the torus decomposition. This is a little more delicate, but the decomposition itself is not terribly challenging. So you look for embedded essential tori in the manifold, injective on the level of fundamental group, but also that cut. So the injective on the level in the sense that they cut the manifold into pieces, each with now a torus boundary component. But there's not a canonical way really to fill in a torus. This is the process of what's called Dane filling. And there's lots of ways to fill in tori. So you just leave them alone, and you don't try to prescribe it beyond that. So now you've got a manifold with torus boundary. And then you can at least formulate the geometrization conjecture, which is that each remaining piece has a complete locally homogeneous Riemannian metric. Okay, so in terms of Riemannian geometry, to say this is any given 2 points, you can find neighborhoods that are isometric of these points. There's kind of a more homogeneous space-oriented way of saying this, which is that you can find a sort of a GX, what's called a GX structure for each of the remaining pieces. So here, once you've done the decomposition, you can claim that each piece can be given as x mod gamma, where x is one of 8 so-called model geometries. Okay, these are geometries which have the property that they're locally homogeneous. And then an action by a discrete subgroup of the isometry group of the model will yield as the quotient the piece of 3-manifold in your decomposition. Okay, so there's a lot to say about this, but what you'll notice is that of the list of model geometries, so this the sphere, 3-sphere Euclidean space with the Euclidean metric, hyperbolic space with the hyperbolic metric, and then some product geometries, S2, and then E1 here is not R because you think of it as actually having a Euclidean action, the Euclidean metric, and likewise H2 cross E1, each endowed with its sort of canonical metric. T1, H2, this is the unit tangent bundles. This is sometimes called SL2R geometry. And then 2 sort of concocted geometries, nil and sol. They're natural enough, but it's not the point of this talk to go into the details. But really all but the hyperbolic case here are pretty standard to understand what the range of 3 manifolds that occur as these quotients. And you'll note that only one of them is compact as a model, S3. And so the Poincaré conjecture follows as a consequence of this, okay? So in other words, if you have a trivial group gamma, which will be isomorphic to the fundamental group, the only one that can be closed after you take the quotient is S3. Okay, so, and I'll just make a comment actually. I don't know if you will all know the news that my dear colleague and friend Andrew Casson recently passed away from cancer. And he was on the faculty at Yale for some 20 years. And a formidable teacher. But he said one thing about this conjecture that really stuck with me, which is one of the central challenges in attempting to prove the Poincaré conjecture is effectively to harness the hypothesis that the fundamental group is trivial. So it's sort of, where do you start? You know, and in some sense, it makes sense that the way to start to approach this is to say what else, give a complete description of everything else that could possibly happen, and hopefully you're left with something that proves the conjecture. He did actually make some progress. Okay, so, and in the case where X is hyperbolic space, gamma has a term associated with it called a Kleinian group. Okay, so this is in the spirit of Fuchsian groups, Kleinian groups, discrete subgroups of the isometry group of hyperbolic space of various dimensions, or in the case of 3 dimensions, these are the same as the Mobius group, PSL2C. Okay, so Thurston's vision, which was set out in a beautiful Bulletin of the AMS paper in 1980 on the mathematical heritage of Poincaré, came with many partial results embedded in it. So first, his comment is that the geometrization conjecture subsumes the Poincaré conjecture, but provides sort of an entry point into the full picture of 3 manifolds, much in the same way Poincaré's work on uniformization of surfaces gave the tools you needed to try to understand surfaces in a really complete way. So he also proved this in the case when you have a compact manifold with boundary for its interior, that you can prove the geometrization conjecture in this case, and so most of these are hyperbolic after you do the torus decomposition. And then likewise, the case of what are called Hawken manifolds. This is named after Hawken, but these are also sometimes called sufficiently large in the language of Waldhausen. So the idea here is that you're looking for ways to get started. So you're looking for surfaces like in the sphere, the prime decomposition and the torus decomposition. You look for another larger surface to cut the manifold along and then do a decomposition and try to solve a gluing problem to find the hyperbolic structure. So what a Hawken manifold is it emits a manifold is Hawking if it emits an embedded, incompressible surface. So there's no closed loop on the surface that bounds a disk in the 3-manifold. And that gives you a way to get started with a decomposition process. So he proved that Hawking manifolds are hyperbolic if and only if they're atoroidal, meaning there's no torus in the torus decomposition. Okay, so this was a big step, and it involved, it included the case, which is sort of demonstrative and interesting to talk about, of the case of the 3-manifold that fibers over the circle. Okay, so you can really think of this as just if you take a surface, the simplest 3-manifold associated with a surface, you just take an interval bundle over the surface, S cross I, and then you can glue one into the other by a diffeomorphism of the surface, and then that manifold naturally fibers over the circle, just as the interval glued with its ends glued together is the circle. You can associate you can create the fibration that way. And so then you can frame the geometrization conjecture in terms of the associated gluing map. So are there tori that result from the gluing of one into the other, and that shows up in the characterization of the gluing map. So, but paradoxically, that was a very hard case to establish, the case of the fibering over the circle. And the comment there was that somehow it's paradoxical that in hyperbolic geometry, where everything seems to be expanding exponentially in all directions, that you have something that can be so regular as a fibration. So you have the surface is really just a bounded distance from each copy. If you unwind this along the circle direction, you have a Z cover of a 3-manifold that fibers over the circle, and each copy of this surface in this cover is a bounded Hausdorff distance from the next. So that seems to sort of be counterintuitive with respect to the expanding dynamics. Somehow you have to embed the expansion of the dynamics in the map of the surface to itself to get this to work. So we'll say a bit more about that as we go along. Okay, so just to kind of refresh everyone on hyperbolic geometry a bit, since I'll be saying a lot about it, the model that will show up in some of the pictures is usually going to be the disk model. Okay, so you take the disk with the metric on the screen there that expands infinitely as r approaches 1. And this allows you to do lots of interesting things that you can't do in Euclidean space, like you can tile, first of all, geodesics in this model for hyperbolic space are either diameters of the circle or circles that are orthogonal to the boundary at infinity, so to speak. Triangles, rather than having interior angles summing to 180 degrees, sum to less than 180 degrees, and you explicitly can relate the area of the triangle to the angle defect. But you can tile things with these hyperbolic triangles, and indeed, this was an early approach to finding hyperbolic structures, is to try to produce decompositions into polyhedra with finitely many sides. And you can also do something else, which is interesting part of the constructions for these hyperbolization efforts, which is to look at ideal triangles, which have interior angles 0. Their sort of vertices are at infinity, and this gives a way to sort of decompose a manifold if you have somewhere to put the vertices. So indeed, in this case where you have an essential torus in the manifold as part of the decomposition, the discrete subgroups isomorphic to Z plus Z in PSL2C are perforce rank 2 parabolic groups. So when you have an essential torus in the manifold, that's naturally a cusp in this manifold. And so you can triangulate a manifold at times with tetrahedra that have one vertex out this cusp at infinity. Okay, so why the interest in hyperbolic structures? Well, one good reason to be interested in them is a theorem of Mostow called the rigidity theorem, which really says that the hyperbolic geometry of a closed hyperbolic three-manifold is a topological invariant. Okay, so if you have two hyperbolic manifolds, hyperbolic three-manifolds, and an isomorphism of their fundamental group, you can construct a homotopy equivalence, according to Mostow, that's an isometry of the manifolds. Okay, so that respects, so where the isometry on pi 1 is equal to your isomorphism. Okay, so all you need to know is that these two manifolds are homotopy equivalent to prove that they're actually isometric. So things like if you have a knot complement that admits a hyperbolic structure, that the hyperbolic structure will have finite volume, okay, and any other hyperbolic structure on that knot complement will be isometric. So the volume itself is a knot invariant. But this is just the beginning. So geometric characteristics of a closed hyperbolic three-manifold, so things like the injectivity radius or the length of the shortest closed loop or the Cheeger constant, all of these sort of geometric notions become invariants of the topology of that manifold. So I feel like this is sort of the inspiration point for a lot of the work in hyperbolic manifolds, is sort of what geometrization doesn't tell us. So it tells us in terms of topological characteristics which things we can expect to be hyperbolic, but it doesn't tell us what that hyperbolic geometry looks like. So ideally, you'd like to start with a topological description of a three-manifold. This can come in various forms. It could be a knot complement or a Dane filling, where you fill back in the torus. Or it could be a three-manifold that fibers over the circle, where you've described the gluing map. Or perhaps a Heegard splitting. There are various ways to describe the topology of three-manifolds. Can you start with that information and conclude effective geometric information about the manifold? And so this has kind of been a motivating ansatz, I guess, for a lot of the work that has paralleled, if you like, the search for the proof of the geometrization conjecture and continues on today. So, but to just give credit where due, I think we all sit around at conferences a bit and puzzle over how much Thurston knew and just didn't write down. Okay, so there's a list of questions in this AMS article that's, just to look back on it even now, is it's almost like seeing a ghost or something. So he lists 20 questions at the end, and I'll list a few of them that seem deeply prescient. But indeed, to formulate and pursue and to prove the cases that he proved in that paper, in the Hawken case, it involved a deep search in the setting of infinite volume hyperbolic manifolds. So you remember I described that if you can find one of these incompressible surfaces, you can cut the manifold, and then you try to solve a hyperbolic gluing problem where you find a hyperbolic structure on the cut up manifold and then glue it back together in a way that the gluing map preserves the structure. So that involves looking around for a hyperbolic structure on this infinite volume manifold that satisfies this. And so there's a great deal of work that he did to understand this. So in in particular, once the Hawken case was proven, it set off an effort to prove the sort of so-called virtual Hawken conjecture, and that was number 16 in his list of problems. So one looks for not a structure, not every manifold is Hawken, but perhaps you can find a cover, a finite cover, where the manifold does admit one of these embedded incompressible surfaces via passing various surgery techniques to arrive at this. If you can do this for various reasons involving topology and the Mostow rigidity theorem, you can prove that gives you a hyperbolic structure on the original manifold. So the motivation for the virtual Hawken conjecture and the work that came thereafter was to solve geometrization. Okay, so then Perelman relieved it of that burden by proving the geometrization conjecture, but it was still very interesting and was resolved in 2012 by Agel. This is just to list some progress since the proof of the geometrization conjecture. Sort of a more general case is called the virtual fiber conjecture. So fibered manifold is Haken because the fiber itself is an incompressible surface. But there was an idea that this also might be interesting and useful as a route to geometrization. Once geometrization is known, though, you can still ask, is it possible that there's some natural way to understand how each hyperbolic three-manifold can be, you can find a cover that fibers over the circle. Why? Because we understand a lot of information geometrically about the fibered manifold, and that may tell us information about the original one. But again, this was resolved by Agel shortly thereafter, I think 2012, 2013. And these two results made strong use of a result that was awarded a Clay Prize, justly, of Kahn and Markovic, that a hyperbolic three-manifold closed hyperbolic three-manifold admits a surface subgroup. So you can find a closed incompressible surface subgroup in this manifold. This had been asked in the general topological category, but the result made great use of geometry, hyperbolic geometry, and dynamics. Somehow there's an idea that you can use the geodesic flow on the frame bundle to find enough pieces of surface, pairs of pants, so to speak, that can be aligned in a way that where the bending is sufficiently small that the result is incompressible. So deep use of hyperbolic geometry to prove what is ultimately a topological theorem. So I suppose that's really the meta information here, is that any question you want to ask about topology of three manifolds now, you have this robust toolkit coming from hyperbolic geometry to help you construct or solve the question. So these, I guess the third wasn't explicitly stated in Thurston's paper, but it was sort of implicit. Likewise, more questions from Thurston's paper. Also the recipient of Clay Prize. The tameness question. So if you have a hyperbolic three-manifold with finitely generated fundamental group, is it homeomorphic to the interior of a compact three-manifold? Now, this is only interesting in the open case, the case of infinite volume. But again, because you're interested in understanding these open cases to solve the closed case, this was relevant, and it came from his search for the solution to the gluing problem through the deformation space. This kind of resolved the question of whether you could have wild ends in the sense of Whitehead in the setting of an open hyperbolic three-manifold. So is it topologically tractable? A wild end is a setting where there's a compact submanifold such that the removal, even though the fundamental group is finitely generated, the removal of a compact subset has infinitely generated fundamental group. So somehow it has finite generation, but there are elements in the fundamental group that have arbitrarily long paths to being collapsed. Likewise, the ending lamination conjecture, which I had some involvement in, is the classification of tame manifolds in terms of invariance called end invariance. It's sort of like a generalized rigidity theorem. It says if you know what's happening at infinity, you can solve for the interior. You can think of it as kind of a Dirichlet problem for hyperbolic three manifolds, where the data are the conformal structures at infinity, or these generalized invariants called end invariants. So these two results taken together were a complete classification of the finitely generated hyperbolic three manifolds. But one that's still really open, and one that I think that goes back to the motivational question I asked, is this question of the quasi-isometry type. Quasi-isometry is a word that gets used a lot in group theory, combinatorial group theory. What is really meant by this here, and this I'm just using the language he used in his paper, is can you build a model for a hyperbolic three-manifold? And by that is meant some way to describe it concretely in a combinatorial way such that in terms of the topological description, so that the hyperbolic structure is bi-Lipschitz to the combinatorial candidate. So imagine you've got these pieces of hyperbolic manifold and you can assemble them in some way so that they admit a bi-Lipschitz comparison to the actual hyperbolic manifold. And this quasi-isometry type question is still very much open. It was necessary to resolve this ending lamination conjecture in the cases that we developed, but that it was incomplete to describe the whole case. Okay, so I guess what I'd like to do is say a little bit just to give you a sense of things in terms of this case of the three-manifold that fibers over the circle and what's hard about its proof, but also how this gives rise to a perspective on what the classification might look like. Okay, so just to back up, we have a diffeomorphism of the surface to itself called psi, and you can build the mapping torus, so-called, by taking the interval bundle and gluing one side to the other using this diffeomorphism. That produces a closed three-manifold if the original surface is closed. Okay, and the topology of this manifold depends only on the isotopy class of this so-called monodromy, this diffeomorphism of the surface. So it's really the dynamics completely determines the topology of the resulting three-manifold and therefore the hyperbolic structure if it's hyperbolic. Okay, so, and this Thurston's search for the hyperbolic structure on this manifold was quite involved and involved developing a whole theory of the possible shapes of limits of so-called Quasi-Fuchsian groups. So I'm going to say a little bit about that. So what he proved in the end can be rephrased in terms, this is basically just the geometrization conjecture, or hyperbolization conjecture in this category, but it's rephrased in terms of the dynamics of this diffeomorphism of the surface. Okay, so what he proved is that this mapping torus is hyperbolic if and only if the monodromy psi is what's called pseudo-Anosov. Okay, so the notion of being pseudo-Anosov in terms of surface dynamics is sort of like you have an affine stretch map in local foliation coordinates. So it sort of stretches in one direction and contracts in another with respect to a singular foliation on the surface. But another way to say it, it's an equivalent characterization, is just that it preserves no isotopy class of simple closed curves. Why might you be interested in that property? Well, if I have a surface and I have a self-map of it that sends a simple closed curve to itself under some power, then in the mapping torus, that will produce a torus, a literal torus. Okay, so you have a curve cross the interval and you glue one into the other, you actually have a torus in that manifold, and that's an obstruction to being hyperbolic. So it turns out that's the only obstruction, and so it's sufficient to consider these pseudo-Anosov mapping classes. Okay, and then this was where, you know, again, his perspective was so broad. He was also interested in understanding the nature and character of surface diffeomorphisms. And as it happens, this pseudo-Anosov mapping class, as I said, you can give local coordinates in terms of singular foliations so that the map can be normalized or isotoped, so it preserves these two foliations as sets, contracts one, and expands the other. Okay, and we see this a lot in Teichmüller dynamics. It's like a Teichmüller translation along a Teichmüller geodesic, if you're familiar with that. But there are these two laminations, or foliations, are really equivalent notions in this setting, the sort of unstable and the stable foliation for the surface. And you can think of in the dynamics on surfaces that psi has the unstable foliation as a repelling fixed point at infinity, and the stable one as an attracting fixed point in the sense of surface dynamics. So these are distinguished isotopy objects on the surface for the dynamics of this map. And the proof of the existence of the hyperbolic structure involves sort of a search through the deformation space of manifolds, of hyperbolic manifolds that have the structure of S cross R for some sort of action that's psi invariant. So if you can find a hyperbolic manifold that's homeomorphic to S cross R and admits a translation in the homotopy class of this mapping class psi, that's a start for finding a gluing or a projection that realizes the mapping torus action. So that's what he decided to do. So I'm just going to say, just so you have sort of a sense of the dynamic and interesting nature of this kind of search process. Again, it's a very different perspective on the problem than Ricci flow, where you're just taking an abstract space of infinite dimensional space of metrics and sort of trying to find the geometric structure in that space of metrics. Here, this is sort of trying to find a geometric structure within the space of hyperbolic metrics that works for your specific topological challenge. Okay, so backing up, the uniformization theorem, if you have a surface X that has higher genus, you can realize this as the quotient of hyperbolic space via a Fuchsian group, okay, discrete subgroup of PSL2R, isom of H2. In this case, you can imagine you're taking the octagon, the regular hyperbolic octagon, and gluing pairs of sides via some hyperbolic transformation of the plane, and the resulting group that you get gives you such a quotient. This is chosen to be symmetric just because it's fun to look at. You can start with anything where the sides match up and perform this procedure, as long as it's a tiling. But we can also think of this as living in hyperbolic 3 space. This is for the purpose of understanding how this picture relates to hyperbolic 3 manifolds. In the same way you have a flat plane dividing 3-dimensional space, there's in the ball model for hyperbolic 3 space, you can imagine that you have a disk that sits at the equator, in effect. That is a hyperplane, a totally geodesic hyperplane in hyperbolic 3 space. And this group that you've used to uniformize a genus 2 surface can act preserving the equator, preserving that hyperplane, producing a Fuchsian hyperbolic 3 manifold that is just the surface cross R with an exponentially expanding metric as you move up or down. Okay, so that's what's called a Fuchsian hyperbolic 3 manifold. How can we deform? So I keep using this idea of searching in the space of hyperbolic, infinite volume hyperbolic manifolds for the solution to your gluing problem. So one way to search or to look around in this space of hyperbolic manifolds is to do what's called bending, just to give you an example of how strange these manifolds can look. If we take the lift of a simple closed curve on the surface, and this is none other than the lift to the hyperbolic disk of the sort of obvious separating simple closed curve on this genus 2 surface, draw the waist, if you like, of this genus 2 surface, that lifts to the blue geodesic in this picture in the universal cover. Now what I want to do is take this nice flat case and introduce a bend along this geodesic. And it turns out there's enough flexibility in hyperbolic space to do this and preserve the discreteness of the action. Okay, so in literal terms, I'm in the upper, forgive me, I'm in the upper half space model now. This red dome is actually also a hyperbolic plane. I'm finding a geodesic and I'm introducing a bend in hyperbolic space. So it changes the angle of intersection between two domes or hemispheres orthogonal to the boundary at infinity. And if you do this sort of infinitely, you would think you would run into trouble in Euclidean space. You would. If you bend planes a definite amount and then you continue and you bend and you bend and you bend, you eventually will self-intersect. But in hyperbolic space, you can do this infinitely, infinite bending along a sequence of parallel, so to speak, lines and produce something that still embeds. And if we do this along the lifts of this blue curve on the surface, we produce a kind of infinitely bent plane. And this is a sort of a one parameter family of angles for exactly this construction illustrated. So you sort of wander through settings where you have discrete groups that preserve all these pictures, a one parameter family of pictures, so gamma sub t. And as you're wandering out to the edge of this, then you start to get close to a region where the process you will have self-intersection of these planes, and the group will no longer be discrete at that point. So that's sort of the boundary of the deformation space of quasi-Fuchsian groups. Okay, so this was part of Thurston. This is actually, the construction is in Thurston's notes, although the computer programs were not. But this was sort of part of his exploration of what do these groups look like, how can I use them to build hyperbolic structures on three manifolds. This was called the Mickey Mouse example because it sort of looks like a Mickey Mouse head with ears on the... When you draw it with pencil and paper, that's about as far as you get as the Mickey Mouse stage. You don't get the Hausdorff dimension, 1.8. Okay. I don't know what's going on there. Okay. So what space are we working in here? It's called the Quasi-Fuchsian space. This is follows from what's called the simultaneous uniformization theorem. It's of Alfors and Baers. So you have the uniformization theorem for surfaces. Turns out you can take not one but two surfaces and find a single Kleinian group that simultaneously uniformizes them. So it's a single Kleinian group that preserves a topological circle and that divides the sphere into two regions, and where the quotient on each of the two regions is a distinct Riemann surface, but it's a single group. So you're left with two Riemann surfaces and an isomorphism coming from the identification with gamma as their fundamental group of their fundamental groups. Okay, so this simultaneous uniformization has this topological structure of a product, the surface. Just take the quotient of each disk, that gives you the surface, cross the interval. That's actually a version of the Tameness theorem, by the way, due to Martin. But it sits in a bigger space of all representations of pi1 of the surface into the Mobius group PSL2C. Okay, so this is the space he's looking around for these structures. So what did he do? Well, he was looking for something that might be invariant with respect to a monodromy action of this pseudo-Anosov map psi. So he constructed a double limiting process where rather than bending or something like that, you change each side via a Teichmüller modular transformation, psi to the n on one side, psi to the minus n on the other. Watch what happens. Hopefully you can extract, and each one of these admits a quasi-isometry in the homotopy class of psi. So you can twist each one of these by psi in a bounded way. What are you doing? Well, you're hoping that as you take a limit, you can uniformly realize that twist as a diffeomorphism and pass to the quotient. So, but there's more than this, which is if you have the right kind of limit, a rigid limit in the sense of Sullivan, that by Lipschitz diffeomorphism can be realized as an isometry, and that allows you to pass to a hyperbolic quotient. So suffice it to say, the limiting process is delicate, but in the end, what you produce is a quotient manifold that is homotopy equivalent to the fibered manifold, And then there's a theorem of Stallings at the time. That was the current technology that says that this is homeomorphic to the original fibered manifold. It's always funny to me that there's this last step where you actually have to actually prove things are homeomorphic. So this is just to say, in the same way that Ricci flow is searching through Riemannian metrics, Thurston was likewise constructing his own kinds of flows to search through the space of hyperbolic metrics to find the hyperbolic structure. And really, there was a deep theorem that was produced along the way. He likes to build lots of extra structure as he's proving these things, which is that this limiting process is very general. So in the original case, we were sending xn to the unstable lamination for psi, yn to the stable lamination for psi. But you can send these to arbitrary points in the boundary of Teichmüller space, which is characterized as a collection of these laminations. And as long as those laminations intersect in a meaningful way, you can extract a limit. So the question that arose then is, are these laminations that are the new invariants for this thing, do they play the role that they do in the simultaneous uniformization of x and y? Can you classify hyperbolic structures in terms of these laminations? So what one sees as you degenerate Kleinian groups along such, as you head out towards such laminations, well, some laminations are just like this, they're the rational case. It has the effect of kind of collapsing along the lifts of a geodesic. Whoops, I missed that one. See if this stays, yeah. Oh, you got a glimpse. Okay, and then there's the other case, which is an irrational lamination. So this is what a lift looks like on the disk. They're hard to draw on the surface. But when you collapse, you sort of mod out by the leaves in this lamination, the circle, it gives you something that's, and this is literally in the case of the pseudo-Anosov map, actually in the punctured torus case, this is the quotient of the circle via that, those dynamics of the stable lamination. So there's a lot of interesting complex dynamics going on here. And then the statement was that indeed these end invariants, these laminations at infinity, suffice to determine the hyperbolic structure once one has accounted for its topology and any parabolics that may be in the mix. So you assume there's no parabolics and you're just talking about a surface, then the statement is that the end invariants determine the structure. This was true for the simultaneous uniformization in terms of the Riemann surface at infinity, and now that's extended to the end invariants. But you need to know first, for a more general statement, that the manifold is tame. So Ian Agel and independently Danny Caligari and Dave Gabai proved that any hyperbolic three-manifold with finitely generated fundamental group is tame. It's homeomorphic to the interior of a compact three-manifold. This was known by work of Bonahan in the cases like the fibered case where the manifold has the homotopy type of the surface. So they'd been around for a while in that sense, and they proved the more general fact. So these taken together prove the classification of hyperbolic three-manifolds with finitely generated fundamental groups. So you should think of these as all of the open, infinite volume manifolds. Okay, so that's nice. It's good to classify things. But how does it have to do with sort of the broad picture of three manifolds after Perelman? Well, it's really an element of the proof that's interesting, which is the way we set about proving, at least the ending lamination conjecture part of this, was to start with the ending laminations and then build some sort of canonical model just from the topological data of the laminations. So you have to think of them as kind of irrational points on the boundary of the hyperbolic disk, and then you build a sort of combinatorial path joining these irrational points And then you prove that that's by Lipschitz to the hyperbolic manifold. And that analogy is literally correct in the setting of the simplest case of the punctured torus. So we were trying to build this quasi-isometry model and then use a rigidity theorem to prove that that gives you the hyperbolic structure. So I guess what I'm going to ask then is, what can we do with this model? Ideally, it gives you information about the manifold. It tells you not only, something about a rigidity that you've classified the manifold, but it tells you information about the injectivity radius, tells you about the volume growth, tells you about the Hausdorff dimension of the limit set, as it turns out. So there's all kinds of moduli of hyperbolic manifolds that this model gives you the ability potentially to detect. Why can you do this? Well, if you know something like that the manifold has a cover that fibers over the circle, you can produce the model just from what we did for that fibered 3 manifold, and then you have the question of, can you transport information back down to the base? Well, so far we don't have good information about what the degree of this cover is. Okay, so we lose that ability to control what the cover says about the base. But this is sort of the broad project. So I think what I'll do is just to say a little bit about how the combinatorial picture works. And this is fairly light reading. So if you look at the surface, let's just take the genus 2 surface, there's a notion of what's called the curve complex. Okay, and I think this is a fairly broadly useful notion. So you look at all the isotopy classes of simple closed curves on the surface, and you can build a graph. Really, the graph is the most important piece of this, where you associate points to isotopy classes of simple closed curves, and they're done sort of color-wise here. And then you join 2 of these points by edges, unit length edges, if they're disjointly realized on the surface. So what Howie Mazer and Yair Minsky proved that this is a Gromov hyperbolic complex. So it's delta hyperbolic, so every triangle is delta thin for some delta. And what you see is you see the laminations, the candidate laminations for the ending lamination theorem as boundary points of this complex. So you wander out along edges that are pairwise disjoint, simple closed curves, and things get very complicated, and you limit to some lamination at infinity. And then the question is, given that you have stability of geodesics and quasi-geodesics in this complex, that tells you some canonical path between points at infinity. So in a hyperbolic space, if I have 2 points at infinity, any 2 quasi-geodesics that join these points are close together. So there's some way to think of that as potentially generating a model for a hyperbolic manifold, and indeed that turns out to be right. So in the simplest case, when you have just a punctured torus, these curves are just rational points. They're just slopes of rational, p times this way, q times that way. And the irrationals, the other ones are just the irrationals, and they're approximated by rationals. So if I'm to build up a hyperbolic 3 manifold with a pair of irrational points as its invariants, I can look at how those irrational points are related in the curve complex, which is in this case really just the Ferry graph, with the note that I've made an exception. Since any 2 curves actually intersect on the punctured torus, I now call intersection 1 distance 1. Okay, so here's what's called the Ferry graph. I join edges if 2 curves have that property that they have intersection 1, and this produces a way of sort of thinking and organizing all the rational points, and a way of describing irrationals in terms of the continued fraction expansion. So I look at something like the golden mean, 1 plus root 5 over 2, and then I say, well, what are the combinatorics in terms of the continued fraction expansion of this irrational? You can sort of read them off in terms of Dane twists along different curves, left, right, and that produces not one, a path through this combinatorial object, and two, a prescription of how to get there in terms of left steps and right steps. You can do this on higher genus surfaces in a similar way. So in the curve complex, if you have a lamination and it intersects a subsurface, there's a notion of a projection to that subsurface. So you sort of surger it along the boundary, and then you can kind of take a tubular neighborhood of the picture, and the boundary of that gives you a curve in the curve complex of a subsurface of y. Okay, so I can start with laminations at infinity and relate them on a given subsurface. And this is really how the model is built. So this is the projection to y of a lamination nu. And just to give you a flavor of what this is good for, there's a notion that in the same way you have bounded type irrationals where the continued fractions are bounded, and that tells you something interesting about the geodesic on the modular surface that heads to that irrational, namely that it stays in the thick part in a compact subset. There's a notion of bounded geometry for these things. So if you have bounded projections of the laminations at infinity, that gives you combinatorial boundedness condition called bounded combinatorics. And if for every subsurface y these laminations project with less than some k, that gives you a way to estimate the geometry of the manifold, and you can prove that it has bounded geometry. This is due to Minsky. Again, this is just a flavor of what models can look like given the combinatorics, and a way to at least guarantee something like bounded geometry, but it actually gives you all the precise information about the short curves as well. Okay, so I mean, there are a range of exciting things happening in this area that are getting into exactly how you estimate these things quantitatively without reference to genus, or with explicit reference to genus. But I just want to mention some really exciting recent work by a student of Ursula Hammerstadt, Gabriel Viaggi, who proved that you can circumvent a number of the compactness arguments in these original works around the ending lamination conjecture to get geometric control almost like the Margulis constant, which is a God-given constant depending only on the dimension. If there's dependence on the surface, it's literally the Euler characteristic shows up in the formula. So there's no step where you have to take a compactness argument here. That's likely to give us a lot of steam in terms of understanding the geometry of these things. Similarly, there's some recent work of David Fruder, Jessica Purcell, and Saul Schleimer giving explicit a priori bounds for the drilling theorem, where you can take something like Thurston's Dane surgery theorem and prove a generalization for tame manifolds. Again, this would be the kind of thing you'd worry about, the constants cascading as the manifold gets bigger and bigger. Likewise, there's a recent theorem of Hensel, Petritsky, and Webb that shows, whereas the original estimates on the delta hyperbolicity of the curve graph were thought to grow with the genus of the surface, that there's an absolute constant for which the curve graph is hyperbolic, 17, as it turns out. It may have even come down since then. So as you're piecing together the constants in the model, we're getting more and more control over all the ingredients to really say some things that are quite explicit. Likewise, there's work that's showing that you can find bounds on geometry and geometric notions like volume in terms of Weil-Petersen geometry that are quite explicit, using something called renormalized volume. There's a notion of renormalized volume as a potential on the Teichmüller space of three manifolds, and you can look at the gradient flow as a way to move through hyperbolic manifolds towards a geometric picture that reduces volume. So these are just some of the elements that are currently ongoing to allay your concerns that Perelman may have done something destructive to the field of three manifolds. I think it's alive and well, and I am happy to answer any questions that you might have about the current state of things. Thank you.